So the other situation where we're going to need to calculate out the moment of inertia for extended objects is if the shape does matter. The way that we're going to tend to deal with this is to say, well, let's start by just going and looking up what the moment of inertia is. For all of these objects, there's going to be a description of what the shape is. There's going to be a description for the axis of rotation. Usually there'll often be a picture that says, hey, make sure this is what you're interested in. And then this is the equation that you'll use to calculate the moment of inertia. So as an example, if we've got a uniformly distributed long thin rod, mass of M, length of L, that's rotating about an axis through the center of the rod that's perpendicular to the axis of the rod. So that's a situation of saying that my rod is spinning around like this about some axis that runs through its center. Then I calculate the moment of inertia of that rod as 1/12 mass of the rod times the length of the rod squared. On the other hand, if what I've got is a uniform solid sphere, mass of M and radius r, that again rotates about an axis through its center, so again, like in this picture here where the axis of the rod rotates through its center, then I calculate the moment of inertia of the rod as 2/5 mass of the rod times its radius squared. What you need to pay attention to, of course, is making sure that you get the right equation, because you know that that's the equation that goes with the shape you're interested in and the axis that's described in the table. Well, what happens if you don't have that axis? So you know that the shape does matter, but you've got the wrong axis of rotation. So let's say that, again, we were just looking at a situation where that table describes the moment of inertia for a long thin rod rotating about its center. But what if we want to know the moment of inertia for a rod that's rotating about a pivot point that happens to be at one end of the rod? Then what we're going to do is we're going to use what's known as the parallel axis theorem. So the parallel axis theorem tells you that you can get the moment of inertia about some other axis not through the center of mass by looking up the moment of inertia through the center of mass and then adding this additional term mh squared. M is the mass and h is the distance from the axis you want, that's this one here, to the axis through the center of mass that you look up. You're going to figure out what this distance h is, look up what the moment of inertia is through the center of mass, then take the moment of inertia through the center of mass plus mh squared. Parallel axis theorem is one of the tools we're going to use. It's still going to let us basically go look up what the moment of inertia is, then allow us to adjust if we want that object but through a different axis. Well, what if the shape matters but the object is made up of multiple uniformly distributed pieces? And so, as we emphasized when we were talking about with the moment of inertia of point particles, is that the moment of inertia for your system is just the sum of the moment of inertia of the individual pieces. So here, mathematically, all we're saying is if you've got a system that's made up of multiple pieces, the moment of inertia of your system is just add up the moment of inertia of piece 1 plus piece 2 plus piece 3 plus however many pieces that you break your system up into. So what this means is that, again, moment of inertia acts just like mass. How do you find the total mass of your system? You just add up the masses of all the individual pieces. Moment of inertia works the same way. And so as an example, let's say that I've got a rod and then I have 2 point masses sitting on the end. And I'm going to let this 3-piece system rotate through an axis through the center of the rod. What I recognize is I've got 3 pieces. One of them is an extended object whose shape matters. Masses 2 and 3 I'm going to treat like point particles. In dealing with the first one, I go look up the moment of inertia of a long thin rod rotating about an axis through its center is 1/12 mass times length squared. So that's going to be m1 times the length of the rod squared. For masses 2 and 3, which I'm treating as point particles, this perpendicular distance for both of them is half the length of the rod. So to calculate the moment of inertia of mass 2, that's going to be m2 times that perpendicular distance, which is half the length of the rod squared, plus the moment of inertia of mass 3 is mass 3 times Again, it's the perpendicular distance for mass 3, which again is half the length of the rod squared. All I've done is calculate out the moment of inertia of the three pieces and then add them together to get the moment of inertia of your system. Well, what if instead of being point particles, those two masses on the end, I now need to care about their shape? When they were tiny, so the distance across masses 2 and 3 was much smaller than the distance from those masses to the axis of rotation. Now as I make masses 2 and 3 bigger, those distances become much more comparable, and so now I do need to care about what the shape of these masses are. So we're going to say that these are uniform solid spheres, and so how do we deal with this now? We haven't changed anything about mass 1 or long thin rod. We're going to deal with it exactly the same way. We're going to go look up its moment of inertia. It is rotating about an axis through its center of mass, so I can use the equation that I'm given in the table. For mass 2, however, now it's a uniform sphere, but it's not rotating through an axis through the center. So the axis that I go look up is an axis that runs up and down through the center of the sphere. That's not the axis that this is rotating about, which means I need to use the parallel axis theorem to calculate what the moment of inertia is for mass 2. The distance h here is half the length of the rod plus the radius of the sphere. And so when I go calculate out the moment of inertia for mass 2, there's the moment of inertia through the center of mass. So a uniform solid sphere, it's 2/5 mass of the sphere times its radius squared, plus mass of the sphere times that distance h. So half the length of the rod plus the radius of the sphere, that gets squared. So both of these terms are using the parallel axis theorem to calculate out the moment of inertia for mass 2 now. Mass 3 is an identical uniform solid sphere that again is sitting a distance half the length of the rod plus the radius of the sphere away from the axis that it's actually rotating around. So I'm going to treat mass 3 exactly the same way I treated mass 2. Go look up the equation to calculate its moment of inertia about an axis through its center of mass, but then recognize that that's not the axis it's actually spinning around. It's spinning around this axis that's a distance L over 2 plus r away, and so calculate out using the parallel axis theorem that the moment of inertia for mass 3 is 2/5 m3r squared. So 2/5 times the mass of object 3 times its radius squared plus mass 3 times that distance h, L over 2 plus r, and that gets squared. As we make systems more complicated, we can end up having more complicated pieces for how we calculate out the moment of inertia of extended objects. But again, the nice thing is that if you can calculate out the moment of inertia of each individual piece, then finding the moment of inertia of your system is as simple as simply adding the individual moment of inertias together.